coming. It looks like today is very popular. We need another data point to figure out if it's because of the topic that we will discuss, which has to do with exoplanets. So I would recommend the cosmologists in the room to pay attention next time. And if indeed it has to do with the topic, perhaps it's time to switch area of the research. Before we start, since this is the first meeting of the semester, I would like to mention the new arrivals at the Institute of Theory and Computation, the ITC. So let me just read very quickly the new fellows that are joining us. Anna Bonacca, maybe you should just raise your hand. Daniel Dorazio, somewhere. John Forbes. Michael Johnson is joining the ITC, but he was at the CFA before. Laura Kreitberg. And she has the distinction of already, although being just 1 week at the CFA, already wrote a paper with affiliation to the ITC. Great knowledge. Joel Leja. There, Caroline Morley.
She'll be here in October.
And then we have a new center that was established down the road, 20 Garden Street. As of this month, it's called the Black Hole Initiative. It's funded for 3 years, $7.2 million from the Templeton Foundation. And we have several postdocs. This is the only center worldwide that is focused on the study of black holes. And 20 Garden Street is the old registrar's office building. Some of you may remember it. It's like a Greek building. And the new postdocs are Paul Kessler, Eric Curel, and Andrea. They're mostly from physics. We will have some astronomers joining throughout the next year. And then we have a few sabbatical visitors. Dimitrios Psaltis, who is at the Radcliffe Institute right now. He's a member of Radcliffe for this year. Freya Lozel, Bob Fischer, who may be here, right here, and Savas Chiapas, over there. And then that is pretty much it for, we have of course visitors that come and go throughout the year. So let me mention the talks that we will hear today. We just heard an excellent colloquium, the ITC colloquium by Raul Monsalve on the frontier of 21 centimeter cosmology that is entering just now the stage of actually being able to detect the signals. So the psychology is changing from setting units to actually realizing perhaps we have detected a baby together with a bathtub water in our bathtubs. And so the first talk we will hear will be by Dave Charbonneau. He will talk about an important discovery that was reported about a couple of weeks ago on a habitable planet around the nearest star, Proxima Centauri B. And if you are thinking of buying real estate, this would be a good place to invest because the value will only go up in the future as the sun will die. Well, actually, the Earth will not be habitable within 1.5 billion years, much earlier than that because of the change in the properties of the sun. We'll hear also from Debra Fischer, that is visiting us from Yale, and she will give the CFA colloquium later today, again about planets. She will talk about what stellar abundance ratios can tell us about planet formation. And then we'll hear from Yuan-Sen Ting, a graduate student in our department, that will talk about low-resolution stellar spectroscopy. And finally, we'll hear again from Raul Monsalve on the effect of polarization in the foregrounds of the global 21 centimeter measurements. Dave. Go ahead.
Tradition has it that before you discover a planet, you have to first discover the star, unless you work in microlensing. So I wanted to show you, the man on the left is Robert Innes, and 100 years ago, he published the following two-pager saying there was a faint star of large proper motion. So what he did is he took photographic plates, he blinked them and noticed that in the vicinity of our closest star, Alpha Centauri, there was a little faint thing that seemed to be moving. And he says, my measurements by blinking, blah, 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 yield a motion of roughly 4.8 arcseconds towards 289 degrees. And he said, somebody else makes a perfectly independent measurement and it agrees with me. And then he notices that, of course, this corresponds within the uncertainty to the proper motion of Alpha Centauri. And so he concludes Alpha Centauri is actually a triple star system. Okay? The primary is a G star, then there is a K dwarf. They're in a relatively tight orbit of something like 77 years. And then separated at some enormous separation, but then gravitationally bound, is this little faint thing, which of course now we understand to be the most common kind of star in the galaxy, an M dwarf. I also bring to your attention that he says the following about the photometry. Neither star is in the CPD, which here goes to the 10.3s, referring to magnitudes. And both are distinctly smaller than 10.3 stars, so that in the CPD scale, the photographic magnitudes would be about 11th, or in the Harvard scale, about 12. So the first instance of grade inflation. Okay, so now I was not surprised to hear that someone had discovered a planet around Proxima Centauri because only a year ago, Courtney Dressing finished her thesis here. Courtney Dressing analyzed the data from the NASA Kepler mission, and she focused on the M dwarfs. Now, these were not M dwarfs like Proxima. These were more massive M dwarfs. M dwarfs range from 1/10 of a solar mass to 60% the mass of the sun. Kepler mostly looked at the massive M dwarfs, so these are about half the solar mass. And what she found was if you restrict your attention to planets that are the same temperature as the Earth, so planets that have the right amount of insulation to land in the so-called habitable zone, where water may be liquid on the surface, and you restrict your attention to planets that are the same size as the Earth, then you find that indeed 1 in 4 such stars, more massive M dwarfs, has a habitable and Earth-sized planet. Okay, very exciting. So lo and behold, the idea of looking for radial velocity signatures around Proxima Centauri is nothing new. People have tried to do this for a very long time, but here we have finally what looks like a very strong signal. And so we have the paper that was just published in Nature, led by Guillem and Glade Escude, who was visiting here only a week ago as part of the Opportunity M meeting that we convened at the Center for Astrophysics to think about the opportunities of finding small, potentially habitable planets around the very closest M dwarfs. What Guillem had done was to look back at other people's data, gathered with both the UVES spectrograph on the VLT and with the HARPS spectrograph, arguably the world's premier planet finder, at least in the southern hemisphere, and had noticed, as others had noticed, that there was a signal popping up in the periodogram at around 11 days, but it wasn't strong enough to claim a detection. And so what he argued was one had to go and observe nightly. And so he arranged for a special thing, which was that they would get an observation every single night on the telescope. And so they did. They got an observation essentially every night in the first 3 months of 2016. Once they do that and they combine with the old data, then that signal gets stronger. That's a good thing. And it appears to be now to have a false alarm probability of 1 in 10 million. So in a nutshell, that is the detection. Okay? So they see a periodic signal in the radial velocities. Now, of course, the reason that they paused before rushing to publish was we have seen planets disappear in the past. So M dwarfs are great at showing us their surface magnetic phenomena. Those features, like spots and faculae and plages and probably things that M dwarfs do that the sun doesn't do, often create a perturbation in the apparent velocity of the star. So when you're integrating over the visible hemisphere of the star, and the star is changing its temperament over time, and it certainly is rotating, showing you some features that are going in and out of view, then the hemisphere-integrated velocity of the star doesn't remain constant, and so you can't assume that because the velocity changes, you're seeing orbital motion. Here is a devastating example of this at work. This was a paper published by Paul Robertson a few years ago. Gliese 581 holds the distinction for having the most independent claims of different habitable planets discovered around the star. So in fact, 3 different times, and we're talking about different planets, not the same signal. And I believe they have all fallen by the wayside. You can ask Professor Fischer. Okay, so 581, that was the darling. There were whole papers devoted to studying the habitability of planets that apparently do not exist. And what Paul simply did was to say, look, the radial velocities are plotted here in blue, and this signal is plotted as a function of time. You can see there's variation, and it phases up, and it's periodic. But if I measure the H alpha, okay, if I take one spectral line, which is really sensitive to magnetic activity, it seems to magically know about these velocities. So obviously that looks bad for it to be orbital motion, right? Okay, so that was the death of several planets around 581. Going back to Proxima, these are the data, the phase-folded data. There's no significant detection of an eccentricity. What they do, though, is they spend most of the paper, and you can read all 14 pages of the supplemental analysis, as I have done several times and will be assigning to my students in 189 for the next lecture. You can see their velocities plotted up top. Then they take various things that would be bad news if they correspond to the change in velocity, such as, for example, the H-alpha absorption, independent photometry from the Las Cumbres Observatory Global Telescope in V and B bands, and then moments of the spectral line. So the spectral line, if it's orbital motion, the spectral line should just go back and forth. If the shape of the spectral line is changing, that would give you a change in the centroid, but would not be orbital motion. That would indicate something not obviously due to an acceleration of the star. And those all change on the time scale of 83 days, which was the known rotation period of the star. But they do not appear to change on the short time scale of 11 days, which is the claimed orbital motion. So in a nutshell, that is, if you want to believe there's a planet around Proxima, which I think the evidence looks pretty good, at least in terms of it being a rate of velocity detection, then that emotional decision in your mind depends on this argument, not the detection of the periodic signal. Okay, so to quickly flash up the numbers, it is exactly a representative of the most common kind of star in the galaxy, an M5 star. It has a mass, about 12% the mass of the sun, and the period is 11 days, and that puts it squarely in the habitable zone. So the equilibrium temperature, the classic calculation we assign in first year kind of undergraduate, puts it at 234 Kelvin. There's been some careful analysis that for M dwarfs you want a slightly lower irradiance because of the cooler photons that are striking the planet. The transit probability is about 1 in 66. So while I was not expected that there was a planet, I would have to re-examine my faith if it does actually prove to transit. Okay, so Mirth. Mirth is a photometric observatory that likes to look at nearby M dwarfs. So I thought I would just take the opportunity to show you that we, of course, have not ignored Proxima. We've looked at Proxima going all the way back to 2014. We have, I don't know if Jonathan's here, some enormous number of observations. And here, if we bin those and then bin them again, you can see a very interesting thing, which is that this is the rotationally modulated amplitude due to spots. You can see very clearly that 83-day rotation period, but the amplitude is increasing. You can actually see that the spot, it's not really a spot, it's the asymmetry in the spots. The amplitude of the variation is going up over time. So I don't think that hurts the planet case, but we have a great knowledge of the star's temperament. If I make a periodogram, or actually, if Elizabeth Newton, who did this work, makes a periodogram, she did this work, Elizabeth finds that indeed we recapture very clearly the rotation period. But the key point is that if you look at the harmonics, the things that you might really worry about as being fake planet signals, you never get down to anywhere near 11 days. The habitable zone, which is bleached out here, begins here and goes all the way out through here, and the detection of the planet is right about here, okay? So independently from Earth, we looks like there's nothing fishy going on at the 11.2 day period. Of course, the big question is, does it transit? Actually, nobody has ruled out transits yet. Mirth's observations are so short, they're less than a second because the star is so bright. We are completely dominated by atmospheric scintillation, okay? So we actually have very large noise compared to what you would expect for such a bright, such a large number of photons. Of course, the MOST satellite in space does not have to suffer from atmospheric scintillation, and I know analysis by David Kipping and Dimitar Sasolov will be released shortly, hopefully giving us conclusive answers to whether or not this thing transits. That's all I have to say.
The obvious question
The last sentence of the paper by Guillaume Anglada Escude gives us some guidance. A warm terrestrial planet orbiting Proxima offers the opportunity to attempt further characterization via transits. So again, that's a 1 in 66 chance. Don't bet on it. By direct imaging, that is possible, right? So if you calculate lambda over d for this planet, recall it's 1.2 parsecs away. The habitable zone is enclosed, but if you calculate lambda over d, you get that you could not really resolve this with the current 8 or 10 meter telescope, but you could probably resolve it with, gosh, a 25 meter telescope. But of course, you're not seeing that it's the contrast ratio that gets you. So it is possible, but the contrast ratio is what gets you. You would have to see the planet probably in reflected light. The thermal emission of the planet doesn't dominate until you get out to around 10 microns or later. So there's actually a lot of construction going on, so I can't hear you, sir. Yes, but it will not have the diameter of mirror, I believe, to resolve Proxima. So it can try to see temporal variations. And I believe you, sir, have published a paper with the aforementioned Laura Kreidberg talking about just that idea to see if you could study the atmosphere. So that's one thing you could do is look for variations in the brightness of the system as the planet makes its way around and say, well, as long as we can rule it that that's due to the star, then that would tell us whether or not the planet has an atmosphere. A denuded planet would show a very large phase variation as you look at the day side and night side. A planet with a thick atmosphere might show no variation. Temperature changes are rather modest in Boston even after the sun sets. Right.
Dave, do you know what the contrast ratio is between the star and the planet?
In reflected light, I believe it would be something like 1 in 10 million.
The temperature of the star is 3,000 K in the planet would be more than 300. So if you go to the right spot, it's only a factor of 10.
Well, no, you have to include the surface area. Yeah. Yeah, so things are, this is always the game we're playing, reflected light. We know how to deal with those photons better, particularly on the surface of the Earth, but the contrast is worse. If you can get out to something like 20 microns, of course, then you're really in space. Then you're just looking at two glowing balls. One is roughly 1/200th the projected area, and it is 1/10th, so it'll be 1 part in 2,000, right, if you're in the Rayleigh-Jeans limit. So really not a bad contrast.
So in the late 90s, there was astrometry done on Proxima that suggested an upper limit for a companion at a roughly 10-day period of about a Jupiter mass. So pretty high value. But Hubble has been upgraded since the late 90s. And I'm curious if there's any idea to follow it up with Hubble to maybe repeat the astrometry exercise now that we know that there's a planet around there.
Yeah, yes, I don't know of any of those plans. Of course, we eagerly await the release of Gaia data as well. Gaia will not visit any particular star at very high cadence, but it certainly does expect to find a lot of companions, not necessarily planetary companions, through the astrometric perturbations of those planets and companions on the central star. So, of course, I think in the case of Proxima, what gets you is, because the planet is in so close, the lever arm on that the astrometric motion of the star is itself just inherently very small. So I don't think that Hubble could aspire to measure it.
I'm guessing that life on this planet would not be a lot of fun, which is to say that it would need to be fairly close, right? Which maybe you will time the lock, so maybe one face is always towards the star and the other one always cold.
Yes, that old chestnut. So, of course, we all understand how life came to be on the Earth and what conditions it can survive under. If you have some doubt in your heart about that level of certainty, yes, it is important to note that the planet is probably tidally locked, so it may have a very highly irradiated day side and an unirradiated night side. Also, Proxima experiences 400 times the high energy flux from its central star than we experience from the sun, so maybe that's bad for life. It may be very bad for the atmosphere, let alone worrying about life. Obviously, it may be possible that in Proxima's youth, when it was even more active, it was very good at blowing off the atmosphere of any surrounding planet that is in such a short orbital period. I think we should measure first and then think. That's my view on this matter. So we should see if there is life and then worry about whether that should be there. That did not escape me.
But I completely agree with you, and actually I asked the G partner the other week whether anyone checked whether there are any radio signals coming from that direction. It turns out that only in 1995 they observed it for 11 hours, and that was it. So if there are if there is anyone there, they can tell us how difficult or harsh.
Right. So maybe just to end, I think that the best near future opportunity to learn about whether such planets have life is to find examples of such planets that transit, and then to use the GMT to go and look for the chemical signature of that life, the waste products, notably oxygen. And in fact, our first light instrument on the GMT is GCLEF. GCLEF actually is sensitive to those wavelengths and at adequate resolution, so it actually could aspire to make that measurement. Now, in the case of Proxima, it probably doesn't transit, but people are thinking about that idea in the context of seeing the reflected light, a more challenging contrast ratio, but more photons because the star is closer.
This optimistic note, let's thank David again.
Do you want this? People tend to talk to this.
Thanks.
Okay,
And this
I'm
is
gonna
on,
steal your
right?
seat, okay?
All right. Yeah, absolutely. All right, so I'm going to talk about some work that's been done by my graduate students. So they really deserve to be, their names are in bigger font than my name is, Jack Moriarty and John Brewer. And it's nice to be a professor and have graduate students coming along whose projects kind of build off of one another. So I get to have this view of telling a little bit about what those two projects, thesis projects, have told us. About the composition of terrestrial planets and how we might use that as we're going forward and looking for Earth 2.0. So I thought I would just put my assumptions up first, because then we can just start arguing right off the bat if there's anything that's wrong here. So first of all, the work that's been done to understand the chemical composition of planetesimals and the planets that form from them are that planetesimal growth precedes this oligarchic phase, right? And the planetesimals are growing locally. And then once they reach into this oligarchic phase where they're large, then they begin migrating and scattering. So that's one assumption that goes in. Another assumption is that we're using equilibrium chemistry. So to the extent that there's non-equilibrium chemistry going on, that's going to affect the answers, right? And you can decide to what level or what order that's important. The third thing is that the abundance ratios in the initial protoplanetary disk are the same as the abundance ratios in the star. And I think that certainly is true for any refractory elements. And we could maybe argue about the lightest elements there. And that the most important ratios for terrestrial planet mineralogy, so now I'm kind of skating out on thin ice on things that I barely know about, are the ratios of C to O and magnesium to silicon. Okay, the idea was laid out, I first read it in 2010 in a paper by Jade Bond et al. And the idea is that when the C to O ratio is very high, above 0.8 in particular, then you get primarily planets that have, the planetesimal material is made up of silicon carbides and a significant amount of solid carbon. And this idea for 55 Cancri, right, the idea that it might have a diamond planet orbiting it was based on the assumption that the C to O ratio in 55 Cancri was about 1. So some people had measured the abundances of these elements in the star, and if the abundance of C to O, that ratio is high like that, then you expect to have mineralogy in the protoplanetary disk dominated by carbon, and you could build up a lot of carbon, which is then under high pressure becomes some kind of a crystal diamond-like structure. Okay, and then for cases where the C to O ratio is less than 0.8, Then the interesting mineralogy is controlled by the ratio of magnesium to silicon. So if the magnesium to silicon ratio is less than 1, the magnesium is locked up mostly in pyroxene, MgSiO3, and the silicon is in silicate, so it's in rocks. If the magnesium to silicon ratio is between 1 and 2, then the magnesium is locked up in olivine, and you have some pyroxene. Okay, so if those, under the assumption that those 4 elements are really important for the mineralogy of terrestrial planets, then those 4 elements are pretty interesting to take a look at in the star. And so then in this work that's been done, the idea was if you start out with a disk of planetesimals, then Jack Moriarty tagged the planetesimals with their equilibrium chemistry. So you take a temperature pressure profile for the disk, right? And with something like HSC chemistry, you can figure out what minerals would form under those conditions. And then you go into the oligarchic phase, now that all the planetesimals have been tagged, and you let everything scatter and migrate around, and you see what the final assembly of the planet looks like in terms of its chemical composition. And then the last assumption is that if we're thinking about Earth analogs, right, Earth 2.0, where things like plate tectonics, which we don't understand very well, are important, then we have a composition that's dominated by oxygen, iron, magnesium, and silicon, with a little bit of aluminum and calcium, but with not very much carbon at all. Okay, so that's the background, and then of course we can start out. We know that planet formation happens over these phases. You start out with a thick disk, first of all. The initial elemental abundances reflect the composition that's you now see in the star. There's a thermal structure. There are chemical reactions that are taking place, materials coalescing onto little grains and transport of material within the disk. And then as the planetesimals grow and form, then there's a timing that becomes important because the disk is evolving, right? The pressure and temperature profile is changing. So you should probably take that into account. And finally, you get down to the stage of embryo scattering. So Jack started out with this idea that there is a temperature profile in the disk, a temperature pressure profile in the disk, and that this evolves over time. And using that and HSC chemistry, he figured out what the mineralogy would look like. The stage was really set by Jade Bond, who really, I thought this was a remarkable paper, or series of papers in 2010, where she studied what kind of elements would condense out in the disk, right, as a function, again, of the temperature and pressure profile in the disk. And what Jack had done was to sort of take this one step further and imagine that the disk is now evolving, and then check to see how that changed the evolution of chemistry and the composition of the planets. And it turned out to have a blank page, an interesting effect in that if you look just at the work that Jade Bond had done, so that's shown here with these dashed lines, she assumes equilibrium chemistry, and she finds out that for C to O ratios over this whole range going from 0.5, which is the solar abundance ratio, down to 1, that you can have carbon-rich planets that are forming out here. And if these guys migrate inward, then they might end up around a star like 55 Cancri. But this C to O ratio that's posted here is the C to O ratio in the star, right? And it's assumed then to be also the initial composition of the disk. And what Jack had shown with his sequential condensation series is that actually if you allow for the changing temperature pressure profile of the disk, you can have carbon rich planetesimals at over a much wider range of separations. That was very interesting. We didn't know at the time what the C to O ratio of stars like 55 Cancri were. So along came my next graduate student, John Brewer, who's just finished his PhD. And in 2005 or something like that, Jeff Valenti and I wrote a paper on spectral synthesis modeling. We looked at a couple thousand stars and quantified the planet-metallicity correlation, and it was pretty good for the time, but one of the things that we did wrong, and Willie Torres has a really nice paper that shows this, is that our spectral synthesis modeling didn't get the gravity right. So John Brewer went through, he actually extended the analysis done by SME by adding a lot more stars. He assumes that astroseismology gives us the right gravity, And then he compares the red triangles are what the Fischer, or Valenti and Fischer results were for the surface gravity of the star, and then his results. And you can see that, his results are agreeing to within 0.1 dex with astroseismology. So no constraints. He's just improved the line list, and he's improved some of the ways that the whole analysis is done. So he has a paper now, which is the spectroscopic property of cool stars. It analyzes a couple thousand stars. And he was able to extend the list of elements that he looked at far beyond what Jeff Valenti and I had done. And in particular, he looks at carbon, oxygen, magnesium, and silicon. And I just put these up here. Sorry, the x-axis should be temperature, which isn't here because it was at the bottom of a panel. But basically, you don't see any very strong trends in the abundances, which I think is a good sign. Okay, so now we've got stockpiled a nice analysis of carbon, oxygen, magnesium, and silicon. Now we're going to flip back to the Bond paper in 2010, where if you look at, she was analyzing a bunch of stars. Some of them had known planets, others did not have planets that were known. And she was adopting C/O ratios from the literature. And you can see that these C/O ratios kind of peak at about 0.7 or 0.8, and there are quite a few of them that extend out, to about 1. So these would be stars that, if they form rocky planets, the rocky planets would have a substantial amount of crystal carbon, diamond centers, right? Diamond cores. And then also she looked at the magnesium to silicon abundances, and these peaked at about, it looks like about 0.8. So I think with at least very self-consistent, and I think better analysis, John Brewer has completed this work. His paper just came out. And it shows the C/O ratio and the magnesium to silicon ratio for these stars. The first interesting thing is that the C/O ratio peaks at 0.5, very much like the sun. There's a nice paper by Jonathan Fortney which said that's how it should be, right? From everything we know about galactic chemical evolution, there shouldn't be a lot of stars that have very high C/O ratios. So that's been confirmed. And then he also looked at the magnesium to silicon ratios. And so these have all been shifted downward from the published values that existed before. And you see this very broad range of magnesium to silicon ratios. So what does it all mean? My last slide. Let's say that we get into this lucky situation where we find 100 other Earths around nearby stars. And we want to decide which are the very best targets to send space probes to, or to carry out observations that maybe take 3 weeks to build up a spectrum of the exoplanet system. Well, I would posit that in that case, we can actually use the chemical composition of the host star to leverage some information. So if the stellar abundance ratios are similar, right, to those in the sun and those on the Earth, the C/O magnesium, silicate, aluminum, and calcium ratios, then it means that those planets are going to perhaps be more akin to our Earth. So I'll stop there. Oh, yeah. Well, that's not the case here, right? So we just have a little thin veneer of carbon, which is perhaps accreted at a late stage. And so I think if you end up with a planet that's really just pure carbon, I would love to talk to people here who are in planetary science about what that means for plate tectonics and energy transport in the planet and things like that. I don't know. I'm sort of would play it safe and say let's go with what we know and try and build from there. So I think there is some merit in looking for planets a little more like our own.
So in the globular cluster environment, of course, the metallicities are different.
Yep.
So would you predict then that
Ooh,
we would
good
have
question.
different distribution of planetary elements?
Yep, absolutely, yeah. So those planets should be quite different, right? Where just Fe on H is low, right? And although we found this correlation between Fe on H and the formation of gas giant planets, that is not borne out for the small rocky planets. And we have the case of Kepler 444, which has 5 or 6 little rocky planets inside of Mercury's orbit. So I think that those metal poor stars probably form planets. And I think it would be incredibly interesting for people who model planetary interiors to figure out what happens when the titanium or silicon to iron ratio is so much higher as it must be in these stars and in the planets that they form. Yeah?
I'm wondering if there's more to this story in the following sense. Herschel measurements that we obtain strongly suggest that a lot of oxygen in the protoplanetary disk is tied up in water ice.
Yep.
So you can have a star with a solar C/O ratio, but the disk with a C/O ratio greater than 1. And so it limits just the extent to which you can infer from the composition of the star. And to Avi's question, as soon as the C/O ratio gets close to 1 and exceeds it,
Right.
you drive carbon
Right.
aggressively into organics. So the sequence is you build up a lot of ice in the disk, which we know is there.
Yep.
And you deplete the amount of gas phase oxygen. You increase the gas phase C/O ratio, and then you drive that C into organics.
Yep. I think that's this is certainly a very simple picture. And I think people who are looking at gas giant planets are thinking that if they look at the atmospheres, once we get good spectra of the atmospheres, they might be able to tell where they're accreting their gas based on, because you have these condensation fronts for C to O and CO2 and so forth. So there's a lot more to the story for sure. Yeah.
It might be a little bit arrogant of us to assume that life was optimized on Earth.
Yeah.
Because it came relatively
Yeah.
early, but in principle it exists in many other environments.
Yeah. Uh-huh. Yeah, okay. So I would have to take a look at that. I know that you would expect the silicon to iron ratio to be much higher in older types of stars, and it certainly has to, be factored into the composition that you would end up in the planets. I mean, it's hard to point to one element, I guess, and say that if the carbon is low or high in the star, that means something about the protoplanetary disk. So I'm very careful to say that we should look at ratios, abundance ratios, that those are the things that should sort of persist. I didn't really answer your question, but I think I don't really know the answer to it.
Thank you very much, Debra.
Sure. Musical chairs. Oh, I'm going to keep the microphone, actually. There you go. There you go.
Hello. Okay. Okay. Good afternoon, everybody. So we heard about planets. And we also heard about the interface between star and planets. So I'm not now going to talk about stars, even that don't host any planets. So I want to talk about stellar spectroscopy. So as more of you know, my thesis focused on something called chemical tagging. So the idea is that if we believe stars that were born together at the same time should have very similar chemistry. So if you can measure many elements and you can find clumps in the chemical space, each clump should show an individual star formation event of the Milky Way. So of course we still don't see the clumps yet, but this should be in the data in near future. So the goal is how do you achieve that? So many surveys are actually pushing the boundary to achieve that, but for chemical tagging, most people believe that you need high-res survey because low-res survey can only measure like less than 5 elements. And there are lots of action going on at high-res. So for example, the 3 survey I circled here are the ongoing survey, and compared to the excellent work, 10 years ago, they are going to collect about 1,000 times more star than 10 years ago. So this field is getting more exciting, but today I want to focus on something different, because what I'm plotting here, the x-axis is the spectral resolution, the y-axis is the target number of star. So you can see that the ongoing survey or planned survey before 2020, there are lots of stars. There are more stars in the low-res survey than the high-res survey. So the question that I try to tackle is whether we really need high-res survey to measure more than 5 elements. Can we measure many elements at low-res? Because if we can do that, then you can increase the sample size by another tenfold. And in terms of chemical tagging, this really matters. And the key is that there are many stars in the Milky Way. So the right panel here, I'm showing the same plots as before. The left panel is the same simulation, but I downsample by a factor of 10. The key is that there are many stars you cannot observe spectroscopically because they are too dim. So if you don't collect all stars that you can observe, the likelihood that you can do chemical tagging is pretty low. So what is the problem about low-res spectra? Why people didn't measure more than 5 elements with a low-res spectra? So what I'm showing here is the typical high-res spectra. As you can see, in high-res spectra, most times are resolved. So people measure elements by measuring, for example, the equivalent width of individual absorption line. But if you go to low-res, most of the lines are blended. And therefore, if you want to measure many elements, the only way to do that is to feed all elements simultaneously, which means you need to feed about 20 to 60 parameters all together. So people thought to build a grid of 20 to 60 dimensions is too expensive. But what has changed in the last 2 years or so is that there are a new cluster of ideas coming out. How do you deal with stellar spectra? So we call out our version the pain is actually to pay respect to Cecilia. Not the paper is really a pain to write, but so of course I have no time to go into the details. But I just want to mention that this is not just another interpolation scheme. In fact, the code is very simple. It's like 100 lines of code, but it's a completely new way to think about how do you fit spectra. And what we have achieved is we are able to fit 20 to 60 parameters all simultaneously. So we can fit full spectra. And another important thing is that in 20D, we actually calculated that it requires 1 million times fewer model than the classical method. So just to show you the pain works, so we actually fit the apogee data. So to be fair, apogee is still in the high res, but I just want to show you that we can fit everything together. So what I've done here is I fit temperature, log G, microturbulence, including 15 elements, and including 12 parameters of line spread function, all simultaneously. And the agreement between apogee and our estimate is really good. And I want to draw your attention to temperature and log G. And what I'm plotting here, there's no calibration in our estimate. So this is just the out-of-the-box results. And the fact that we can get the temperature and log G on the right scale without calibration show the importance of fitting everything simultaneously. And in fact, there are more things that are more important. Like here, I'm showing the apogee result. The y-axis, I'm plotting the spectral temperature versus the isochron temperature. So in some cases, if you have astro-seismic log G, you can calculate their isochron temperature, which is thought to be more precise. You can see that for apogee DR13, there's a big discrepancy between the spectral temperature versus the isochron temperature, and this has a trend as a function of metallicity. So what this shows is that the apogee estimate is systematically too hot for the metal-rich star, which means they actually overestimate the elemental abundances for metal-rich star. So if you fit everything together, the trend goes away. And to be fair, we still have a 50 Kelvin of offset, but this is actually pretty small compared to all results. And the log G that we derive just out of the box is right on the right scale compared to the astro-seismic log G. So this is just to show that the pain works, but I just want to go back to the low-res case. So now we can fit all parameters simultaneously, which means you can fit for the blended lines. So in principle, you can extract information from the low-res spectra. So we study, so in terms of next generation of spectroscopic survey, it's important to understand, do you really need high res? So what I'm doing here is do a simulated study to understand how the uncertainty of elements decrease as a function of spectral resolution. So if you assume the same exposure time and the same number of CCD pixel, and if you assume you have robust synthetic model, what I'm showing here is that the uncertainty is relatively flat as a function of resolution. And we achieve that because low-res spectra just simply afford a higher signal-to-noise given the same exposure time. And given the same number of CCD pixel, the low-res spectra can cover a larger wavelength range. So the important take-home message is that if you have robust model, there are actually not much gain going beyond R of 1,000. So this is going to be very exciting because this means that now we can reanalyze low-res archival data and derive many more elements from the low-res data. But of course, there are also many interesting data coming in. So for example, the Gaia is going to release their first 5D astrometry data next week. But Gaia also have a subset of stars that have really kind of good signal-to-noise low-res spectra. So they have a radial velocity spectrograph. So we know that high-res spectra can typically observe 40 elements in optical. So the infrared is about 20 elements, but we actually calculated that even for Gaia, you can measure about 15 elements with very small wavelength range with this method. So what this means that in the next few years, we will have like few millions of stars with 6D phase space and with 15 elements. And in fact, you can calculate that the Gaia is only measuring 15 elements because they have only like 40 nanometer of wavelength chunk. So if you go to the BOSS, like the BOSS survey, they have a larger wavelength range. By fitting all things together, in principle, you can measure more than 40 elements with low-res spectra. So I just want to conclude by hashtag. So low-res spectra is going to be very cool because they will measure 10 million stars. And to extract information from low-res spectra, you need full spectral fitting. And the important point is that if you have really good synthetic model, there seems to be not much gain going beyond R of 1,000. Thank you. Yeah, sure. Yeah, you can do that. These are tricky. So the study that we make, we only study the elemental abundances. For radial velocity, we haven't really done a detailed study. So what is the theoretical achievable velocity that you can get from low-res spectra? But this is the work that we are exploring now.
Hi, I noticed that the temperature low end was only 4,000 degrees. Do you have any plans to extend down to the M north?
Yes, so we can actually do that. So the problem now is that when you use the pane, basically you're defining a Taylor sphere, and we find that the Taylor sphere for 4,000 to 5,000, you can encompass the whole range with just one model. But if you want to go to different range, you need to have different sphere, and how to stitch them together is a problem that we have some idea how we want to do that, but it will go beyond the pane. That requires some new neural network things. Yeah, the new pane. Yeah. Thank you.
Hello, everyone. Thank you very much for the opportunity. It's a pleasure to be here. My name is Raul Monsalve from the University of Colorado Boulder and also still participating with Arizona State University. So I will talk about polarization effects on global 21 centimeter measurements. And what we are talking about here is cosmology. So this is a slide showing the evolution of the universe from the beginning at the top with the Big Bang, then the release of the CMB 380,000 years after that. And between that and the current universe at the bottom, we have several stages that broadly we can define as the Dark Ages, cosmic dawn between roughly redshifts of 30 and 14 or around that number, and then the epoch of reionization that ended around redshift 6 when, when the intergalactic medium went from neutral hydrogen completely to being an ionized medium. So we have some constraints on the epoch of reionization, but we want to probe what happened before that. And one of is to understand the physics, to understand what effect the first sources had on the intergalactic medium, what were those first sources, and when things happened, all of that. So an alternative for studying all that is using the 21 centimeter line because we are talking about neutral hydrogen, atomic hydrogen in the early universe. So 21 centimeter line comes from the ground state of neutral hydrogen, the hydrogen atom. So you have essentially two ground states, the upper ground state of the hydrogen atom and then the lower ground state. And they are, the difference is that in one case, the upper ground state, their spins, the spins of the proton and electron are parallel, and in the other case, the lower ground state, they are anti-parallel. So when the transition happens, there is 21 centimeter radiation emitted from the atom, which corresponds to 1.4 gigahertz. So if we were observing that from the sky just in front of us, at zero redshift, we would measure 1.4 gigahertz, but when we look back in time to redshifts higher than 6, for instance, we would need to probe the frequency range, or frequencies lower, frequencies lower than 200 megahertz. So another reference is redshift 35 corresponds to a frequency of 40 megahertz. So probing ranges between 30 and 6 in redshift corresponds to probing frequencies between 40 or 50 megahertz and 200 megahertz. And that's the VHF range. That's the range where FM radio is and other transmissions, satellites. And so we need to deal with all that contamination when trying to do this measurement. This is a model for the global redshifted 21 centimeter line from high redshifts. So at the top you have redshift values, and at the bottom you have frequencies connected, as we said before. So there is an absorption feature at high redshift down to 30 and between 30 and 15 expected, and there's an emission feature above expected above frequencies of 100 megahertz or redshifts lower than 15. So, but the amplitude of that expected signal is in the millikelvin range. Also, when trying to probe this signal, very small, very a weak signal in the millikelvin range, we need to deal with foregrounds, in particular galactic synchrotron radiation. And here I'm showing you two full or almost full sky maps at low frequencies, in particular the one at 45 megahertz up there. You can see the temperature scale. We're talking about thousands of kelvins, and we need to go past that and have instruments calibrated at the millikelvin level with high dynamic range, because we also need to get past the foregrounds. So on top of that, foregrounds are somewhat polarized, and these are recent results from the MWA experiment located in Western Australia, and these are patches of the sky, roughly 25 by 25 degrees, and they indicate that the sky is polarized at the 1% level, and I'm talking about the foregrounds. Foregrounds are somewhat polarized. The cosmological signal is not polarized, so polarization in the foregrounds is another aspect of this measurement. Okay, so I participate in an experiment called EDGES. It stands for Experiment to Detect the Global EOR Signature. and it's a collaboration between Arizona State University and Haystack Observatory. It's located in Australia, Western Australia in particular. So EDGES only measures Stokes I because it's a single polarization antenna. We measure this with single antennas. They can measure the global, the sky average brightness temperature, which is what we need. So it's a single polarization antenna, and it only measures Stokes I, anticipating a low impact of the polarized component of I due to the foregrounds. So preliminary simulations indicate that the impact of foreground polarization is at a level lower than 10 millikelvin in the EDGES low band frequency range between 50 and 100 megahertz, and of order 1 millikelvin in the range 100 to 200 megahertz. So this is after our process of fitting for the foregrounds and trying to get to the sensitivity level required for the cosmological signal. So this is a realistic simulation, and it's done averaging the dot product between the antenna polarization and the sky polarization from these measurements from MWA. So realistic assumptions have been used to get to these results, to these expectations for the polarization impact on a system like EDGES. But we are working on extending this simulation, producing synthetic full sky polarization maps from the data. From these small patches, you can go to the angular power spectrum and then generate synthetic polarization maps for the full sky. We are also starting to use simulated polarization maps using the Hammurabi code available since a few years ago for that simulates diffuse foreground polarization for the full sky. And we are using some other techniques to project the polarization of the sky to our antenna, okay? In particular, a technique presented in a paper by Neven et al. Last year working on MWA. I also participate on a project called DARE, the Dark Ages Radio Explorer. This is intended as a precision cosmology experiment. It's led by Professor Jack Burns from the University of Colorado Boulder, and it will be proposed to NASA in December this year. It's designed to observe 1,000 hours from orbit above the lunar far side, because that's an ideal observing environment due to the lack of ionospheric effects. When observing from the Earth, we need to deal with the effect of the ionosphere that is between us and the sky. And also, behind the moon, we will be protected from radio frequency interference. So that's one of the main drivers for having an instrument behind the moon. We will be applying the lessons from the ground-based EDGES experiment. And so for there, the differences with EDGES, for instance, is that there will measure polarization directly. It will be capable of measuring all Stokes parameters. And that's similar to the capabilities of the LIDA experiment that you should know. It's an experiment led from Harvard by Lincoln Greenhill. And so there, in addition to being able to measure polarization directly, it will use rotation of the spacecraft to modulate foregrounds, both unpolarized and polarized, to distinguish the foregrounds from the cosmological signal. The resulting modulated signal contained in Stokes Q, in this case, does not contain the cosmological signal. In other words, by doing this rotation, you will be able to extract only the foregrounds, both polarized and unpolarized, and that do not contain the signal. So you can subtract that from the direct measurement that does contain the signal, and and you can put strong priors on what the signal looks like by having this extra information from modulation. So preliminary studies indicate that tight requirements on the beam properties. You need to know the properties of your antenna beams extremely well to be able to apply this technique, especially the elongation and bifurcation characteristics of your beams. And people at NRAO, in particular the grad student Bang Nang and Richard Bradley, are implementing this technique with a ground-based prototype. They will have an instrument depicted there in the figure that will be looking, it will not be rotating, but it will be looking at the north celestial pole, So the beam will stay fixed while the sky rotates, and stronger and weaker parts of the sky will go in and out the beam, producing a modulated signal. And so they are testing this technique, ultimately used for there, to see whether to what level they can separate the foregrounds from the cosmological signal. And so we are addressing the polarization issue of the foregrounds, trying to measure this cosmological signal at the millikelvin level. Thank you very much.
So I think, did I mishear? You said 1% polarization from the foregrounds. Did you say 1%? Because I thought the galactic synchrotron foreground would be more highly polarized.
Well, so here, this is a measurement from MWA. And here you can see that, so on the left, you see the polarization intensity. And the scale goes from 0 to 10 Kelvin. But the 10 Kelvin is achieved only at specific regions. The average over that map is of order 4 Kelvin. Now, that area of the sky is particularly highly polarized. So it does not represent the full sky. The full sky polarization is even lower than that. Now, the unpolarized component is of order, at that frequency, which is 154 megahertz, is of order 400 Kelvin. If you compare the average of that map, which is 4 Kelvin to 400, that is 1%. And most of the sky is polarized to even lower levels. So on average, 1%. There are areas with slightly higher polarization. But yes, thank you.